This is Donna Nelson at the University of Oklahoma. This is a lecture for my organic chemistry class. And so this lecture is going to be the fourth and final lecture on aldehydes and ketones from chapter 19 in David Klein's organic chemistry book. So here we're going to look at carbon nucleophiles. The vast majority of this lecture will cover carbon nucleophiles. We have already covered oxygen, nitrogen, sulfur, and hydrogen nucleophiles, so now we will finish up the set by looking at carbon nucleophiles. This is going to be a very important group of reactions because you're going to have attack at a carbonyl carbon by a carbon nucleophile. And that means it's going to involve a new carbon-carbon bond formation. Now, if you'll think back, you've had only about 3 or 4 carbon-carbon bond-forming reactions previously. So this is going to be a very important group of reactions which you can add to that list. Then we'll look at the Baeyer-Villiger oxidation. That is not attacked by a carbon nucleophile at a carbonyl, but it is an important reaction of carbonyls. And then we'll look at some synthesis strategies, and that will be the end of chapter 19. So let's start. Let's look at our first reaction. So you are familiar with Grignard reagents, such as is shown right here. And a Grignard reagent, remember, provides an alkyl anion. You can think of it like that. And it's not really an ionic compound, but you can think of it as an ionic compound. And it's just fine when you are predicting its reactivity or its mechanism. It's fine to regard it as an ionic compound. The carbon-magnesium bond does have a significant amount of ionic character. And so, here, in the first instance, you can think of methyl anion attacking the carbonyl carbon. The pair of electrons on carbon will populate the antibonding orbital of the carbonyl pi bond. And the same thing here. Now, in this case, this is not a symmetrical carbonyl because you have a propyl group on one side and a proton on the other. And so you will get a chiral carbon generated. But this is going to be racemic because the methyl anion can attack from this side or the back side. Now remember, the antibonding orbital is going to have 2 lobes. They're going to both be down here. One will be coming out at you. The other one will be going back behind the plane of the screen. And so the methyl anion, the pair of electrons on carbon, could populate either lobe, the one that's coming, the unoccupied antibonding orbital that is coming out at you, or the backside lobe of the unoccupied antibonding orbital. So you'll get both isomers here because either face of the carbonyl can be attacked. And notice it is a new carbon-carbon bond formed. You've actually seen this reaction before in the synthesis of alcohols, so that would be chapter 12 of Klein's textbook. You've seen that before. Here is the mechanism. You can see the pair of electrons coming in and populating the antibonding orbital, helping to break the antibonding orbital of the pi bond. And so the pi bond, a pair of electrons in the pi bond, moves out onto oxygen. Now oxygen bears 3 non-bonding pairs and a negative charge, which then picks up a proton when this reaction is neutralized. And then you have formation of the alcohol. The second carbon-carbon bond forming reaction is the reaction with hydrogen cyanide. So once again, the carbon is going to attack the anti-bonding orbital of the carbonyl. Let's look at that reaction. So here, remember, hydrogen cyanide is somewhat acidic, and so you have cyanide generated. There's a pair of electrons on carbon, and it comes in and attacks, it populates the anti-bonding orbital of the pi bond, which helps to break that pi bond. The pair of electrons moves out onto oxygen. So now oxygen has 3 non-bonding pairs and a negative charge, and then it abstracts the proton from hydrogen cyanide, and thereby the alcohol is generated. This particular compound, since it bears a hydroxyl and a cyano group, is called a cyanohydrin. Now we have under basic conditions, potassium cyanide is usually added along with some hydrogen cyanide. So you want there to be more cyanide than the H+, and so both of these are added. And you can see the same reaction is taking place, the same reaction that we saw in the previous transparency. And once again, it's occurring down here. So it can occur with either aldehydes or ketones. The reaction is good for either type of molecule. The cyano group can be changed to give you an amino group, or it can be reduced to the amino, or it can be hydrolyzed to give you the carboxylic acid. So you have some flexibility here. This is the primary amine. This will be the carboxylic acid. Now, a different type of carbon-carbon bond formation is the Wittig reaction. It's an extremely important reaction. The carbon skeleton is modified. It is increased by, it could be differing numbers. It depends on how large the carbon chain is here on the reagent. And so here you have, for convenience, this is a symmetrical ketone, another symmetrical ketone. Either one of these can react with the Wittig reagent, and notice in the product is an alkene, and it simply looks like these two parts. This part of the ketone is reproduced over here, and this part of the Wittig reagent is produced over here. And so the new pi bond is formed between those two carbons. And so it appears to be a very simple reaction in your mind. It can be very simple. The carbon-carbon double bond is formed, but we will go through the mechanism, and it is not quite as simple as it looks. But I'm not convinced that it is completely necessary for all of you to memorize the mechanism. It will be important for you to know the reaction, the reactant, the reagent, and the products. It's very simple. So this carbon from the carbonyl and that carbon from the Wittig reagent are simply fused together to form a double bond. Now, you will not always be given the Wittig reagent. You might have to synthesize it, and so you will have to learn how to make the Wittig reagent, or how the Wittig reagent is made. So here, the Wittig reagent is an ylide. So an ylide simply has a negative charge and a positive charge on adjacent atoms, and that means atoms that are actually bonded together. And so you actually have resonance stabilization in the Wittig reagent. So the pair of electrons on carbon can be donated onto phosphorus, and you have a carbon-phosphorus double bond. Notice this is a neutral compound. It has negatively charged carbon that can do the attack on the carbonyl, and then a positively charged phosphorus. And so this is going to do a 2 plus 2 cycloaddition between this double bond and the double bond of the carbonyl. You can think of it as a 2 plus 2 cycloaddition. So here is the 2 plus 2 cycloaddition. The carbon with its negative charge does an attack on the carbon of the carbonyl, forming the carbon-carbon bond, and phosphorus is attacked by the pair of pi electrons on the oxygen. And so now this is a 2 plus 2 cycloaddition. If you think of this as a pi bond, thinking of that resonance structure. And so now we have the oxaphosphatane. I don't think that it's necessary for you to learn the name of this class of compound. You will never see it again. This is the only place that you will see this molecule generated. And this molecule is fairly short-lived. So it's not something that you're going to have a lot of exposure to. And so then, once these two bonds are formed, these two bonds of the four-membered ring are formed, then you have the other two bonds broken. So you have two new bonds formed, and the two previous bonds are broken. And so here it's called a fragmentation, and you can see the electrons are drawn to show this phosphorus-carbon bond breaking and this carbon-oxygen bond breaking. So the two bonds that are broken are the two bonds from the original reactants. The carbon-oxygen bond is broken, the carbon-phosphorus bond is broken. So you can see that over here. Here are the new products. You can see that the carbon-carbon double bond has been generated and the phosphorus-oxygen double bond has been generated. So you may recall I mentioned that you will need to know or to be able to predict how to synthesize the Wittig reagent. The Wittig reagent comes from an alkyl halide in which the phosphine, a pair of electrons on the phosphine, does an SN2 attack on carbon to displace bromide. Hence, the carbon-phosphorus bond is formed. And notice, you only have two substituents on carbon here, and so here you have three. So this is going to be deprotonated. So this piece, the CH2, comes from the alkyl halide. This part, you can look at it as this part, is coming from the alkyl halide. So you need to choose the alkyl halide that will give you the appropriate alkyl group in the Wittig reaction. If you need to have a butyl on here, you'll need to have a butyl group in your alkyl halide. So here you simply have a base that's going to deprotonate, and that generates the negative charge on carbon. Here the phosphorus is bearing a positive charge because it donated a pair of electrons to form the carbon-phosphorus bond. Then you deprotonate using a base, and that generates a negative charge on carbon. This is your Wittig reagent. Now, this is very useful because it can install a carbon-carbon double bond, but it is not completely stereoselective. So in other words, here you can see that the Z isomer is the major isomer, but you are going to have some of the trans compound formed. So here you can see this is cis. You're going to have some of the trans compound formed. In the just simple Wittig reagent, the cis reaction is formed. Obviously, it's not the more stable of the two isomers, but if the transition state is analyzed as the reaction is going through the transition state, the lower energy transition state is leading to this higher energy product, and we're not going to analyze that, but that is the reason. You do have the higher energy product here when this is just a simple alkene. If the if the Wittig reagent has stabilizing groups on it. So back here, this is just like a simple alkyl group, okay? No stabilizing groups, and so you get the cis product or the Z product. Now you have a stabilizing group. This can stabilize a negative charge. This can stabilize the negative charge. Remember, in the ylid, this carbon is bearing a negative charge. The other resonance structure, this carbon is bearing a negative charge. If that negative charge can be stabilized by an aromatic ring or by an electron withdrawing group, then you get the more stable product as the major product. So here the trans product, the E product, is the one that is preferred when you have a stabilizing group. Similarly, this other reaction, which is similar to the Wittig reaction, the Horner-Wadsworth-Emmons reaction, and it's different because instead of having the 3 phenyl groups on phosphorus, you have a double bond oxygen and a couple of methoxy groups. However, the reaction proceeds through the same mechanism. So I don't think we're going to need to go through that mechanism. And you also have a stabilizing group on here. So this is very similar. This is very similar to the Wittig reagent that has a stabilized group on it. So you can think of this as functioning as the same way that a stabilized Wittig reagent functions. And so you're going to get the product will be the trans product, the more stable E product. I don't think that it's going to be necessary for you to know the Horner-Wadsworth-Emmons name. Just recognize that this is going to become attached. It's going to replace the carbonyl. Okay, so let's pretend that you wanted to synthesize this product. So this is your target molecule. You could start out either with the ketone furnishing this piece of the carbon-carbon, this piece of the product, and the Wittig reagent furnishing the other part, or the ketone could furnish the part on the right, and the Wittig could furnish the piece on the left. So either route would work. One of these will be superior. So let's look at this. Here methyl halide would be the alkyl halide that would furnish this methylene to the Wittig reagent. Here, this sec-butyl group would be on the alkyl halide that would be furnished to the Wittig reagent. And since this is more sterically hindered, this is more sterically hindered, and you need to do an SN2 reaction here to displace the halide. Here you'd need to do an SN2 reaction to displace the halide. So the top reaction is going to be favored. So we go back and look at this, and you can see that the alkyl halide furnishing this Wittig reagent is going to be less sterically hindered than this alkyl halide, which would furnish this Wittig reagent. And so this one is going to be preferred because of the steric hindrance at the reagent necessary to give this Wittig reagent. So this is the one that is preferred because when the triphenylphosphine comes in and does a backside attack, displacing iodide, and then using butyl lithium to abstract a proton, this is the Wittig that is generated. This incurs less steric hindrance to generate this Wittig than the other Wittig reagent. And so then when it reacts with this ketone, here is the product that was the target molecule. Your final reaction in this chapter 19 is the Baeyer-Villiger oxidation. I'm not certain that it is extremely important for you to remember the name Baeyer-Villiger, although it's probably a little more important than in the Horner-Wadsworth-Emmons reaction. This name is less important to remember than the Baeyer-Villiger oxidation. Notice the Baeyer-Villiger oxidation, you are inserting an oxygen next to the carbonyl. And if you look at the reagent that you're using to insert that oxygen, this is a carbonyl peracid. You have used these before. Metachloropurbenzoic acid, MCPBA, as a way, which is that same reagent, or it fits that same class of molecule. That was a way to, for example, convert an alkene into an epoxide. In other words, convert a double bond into the three-membered ring containing oxygen. So this is the same reagent. So if you remember in that epoxide formation, we were using the carboxylic acid peracid, and remember the oxygen that was used to form the three-membered ring was the oxygen that was bearing the proton. It was not the oxygen attached to the carbonyl. And similarly here, the oxygen that is introduced to form the ester is not the oxygen that is attached to the carbonyl. Once again, it is the oxygen bearing the proton. It is the oxygen bearing the proton. So whenever you see a carboxylic acid, a carboxylic peracid, as opposed to a carboxylic acid, a carboxylic peracid means that there is this peroxide linkage here. You have this extra oxygen. And the one that's in red, the one that's actually bearing the proton, is the one that is more reactive each time. This is the one that's going to actually do the oxidation. And so you can see this oxygen bearing the pair of electrons. It comes in for attack at the the antibonding orbital. It populates the antibonding orbital and helps the pair of electrons in the pi bond move out onto oxygen, so the pi bond breaks. Now you have the carbon-oxygen bond formed. So here is the bond in the product that has been formed in this first step. And then you have an internal rearrangement, the pair of electrons on the carboxyl oxygen plucks off a proton. That pair of electrons moves in, satisfies the positive charge on oxygen, and then you have so this is going to be a nice neutral leaving group now. And so when the pair of electrons on this oxygen moves in and reforms the carbonyl, you have a migration of a group that is attached to carbon, migrates over to the original oxygen that is so active. And so the one that did the original attack. So it now accepts a group migrating from the original carbonyl carbon. So it migrates, becomes attached to oxygen, and you see the carboxyl group depart. That becomes the nice, neutral, stable leaving group. And so here now you can see that the ester has been formed. Now, if this reaction is depicted with a ketone, if actually the starting material is an aldehyde, this is just as successful. And if the starting material is an aldehyde, then here you have migration of hydrogen to form a carboxylic acid if one of the groups is hydrogen. So if you have an aldehyde, the final product is a carboxylic acid. That's the group that migrates. So here is, you can see this can be used to form a ring expansion. You've gone from a 5-membered ring to a 6-membered ring so that the oxygen is in the ring. For an aldehyde or an unsymmetrical ketone, you'll have to make a decision which group will migrate. The one that migrates, here's the order of migrating preference. So notice that hydrogen comes before any of the others. So hydrogen, probably because of its size, the smaller groups have a slight preference to migrate frequently, and so here the hydrogen is going to migrate. Other than that, this is going to be in the order of what can bear actually a negative charge better. So here you have this coming in, this is migrating with the pair of electrons in the carbon-carbon bond. The pair of electrons in the carbon-carbon bond is also migrating. So you have the pi bond formed. The alkyl group is migrating with its pair of electrons over here. And then that pair of electrons is departing with this oxygen. So in the migratory aptitude, what it is the hydrogen, H-, the hydride, it migrates easiest, then it's tertiary, secondary, primary, and then methyl is least. So here you see the ordering listed again, and you can see that in this reaction, the more highly substituted group has migrated. Now, this is with an aldehyde, and when you have the aldehyde as the reactant, the hydrogen, H-, migrates preferentially. So this is the migratory preference listing. When you're designing a synthesis, Carbon skeleton changing is very important. So the first thing you need to look at is there a change in the carbon skeleton? That's the first thing that one needs to consider in designing a synthesis. And so you have some new carbon-carbon bond forming reactions with carbonyls. Actually, you had this before in chapter 12. This one is new, reacting with cyanide, and this one is new, reacting with a Wittig reagent. This is a nice review sheet for you. You can go in and print this off from the PowerPoint file that is available to you for this lecture. All of these reactions you've already had. This sort of reaction you had in chapter 7, reactions of alkenes you had in chapter 8, reactions of alkynes, chapter 9, reactions of alcohols, chapter 12. And so now you've got all these reactions of carbonyls to add to your list of reactions that help with synthesis strategies. And finally, this is a nice review of reactions. These are the reactions that we've seen carbonyls can undergo. So this is a review of the reactions that you've had in this chapter, chapter 19. And so once also, you can print this PowerPoint slide off and use it as a study aid to help you be able to remember these reactions. Many of them will form groups, like this is one large group. So you can go through here and you can see the oxygen nucleophiles, the sulfur nucleophiles, nitrogen nucleophiles, hydrogen nucleophiles, and the carbon nucleophiles, and then the Baeyer-Villiger reaction. So that should be organized very logically for you to help you learn it. So this little review sheet concludes chapter 19. This is the end of the 4th lecture for chapter 19. So it concludes the lectures for chapter 19. So